You start with the applause. You don't know what you're getting into. All right. Okay. Thank you so much, Stratis and also Thomas, for inviting me here. It's really a pleasure to be in sunny, beautiful Amsterdam. It's almost like California. So, all right. So I'm very badly jet lagged. So it will be a fast-paced talk because I will try to keep myself awake. So I hope you will stay awake too. All right. So. Okay, beyond supervised driving. So I like to start with why do we care, right? It's like, why do we even talk about autonomous driving? You know, we're in Silicon Valley. We like TRI want to change the world. It's like, why? You know, this is a small town in Bulgaria. It's called Kula. Has nice, charming little ancient ruins and things like this. It has 3,287 inhabitants. Does anybody know why 3,287 is an interesting number? All right. There's the first part of the talk that's a bit similar. Okay. The reason is that's the annual, so that is the per day number of deaths on the road, right? So that's the number of traffic fatalities per day. So per day in the world, that entire city gets leveled. All right, so that's why we care. There's 20 to 50 million people that are injured every year on the roads. So that's what we're trying to work on. And as Toyota is the #1 car manufacturer in the world, with 100 million cars on the road, something like 13% of the cars in the US, we really care about these things, and we can do something about it. Okay. So what we do, before I dive into the technical details, just want to introduce us because we're fairly young. We're a company, so TRI Inc., like Toyota Research Institute Inc. I know it's a bit weird, but we're created 2 years ago by Toyota with founding of like $1 billion. And we work on autonomous driving, robotics, and material science. For autonomous driving, we have two main products we're working on. One called Guardian, where you drive, but the autonomous driving system drives in the background, and whenever something bad is about to happen, it can alert you, nudge, or take over. We have Chauffeur, which is the normal like level 4 or beyond autonomy, and you have also robots for the aging society. So I won't go into as many details about like TRI or as much like business blah blah that I did at the World Summit AI. We do a lot of stuff. Okay, that's kind of like a high-level summary of the stuff we do. One thing of note that I'll mention is recently we got $2.8 billion more thanks to a demo where we showed some of the things that precedes what I'll talk about today. We spin off a new company in Japan called TRI-AD that will do the advanced development, so basically the transfer of our technology, of our research to the production cars, and Toyota does the production. We're also going to do demos at the Tokyo Olympics in 2020. So some of the things you see here will be in that car and other cars at the Olympics, and also in robots. So just some details about Guardian and Chauffeur. One thing that's important for AI and machine learning is it's the same system. We want to basically the perception, so the computer vision, the prediction, the planning, right? They are the same. What differs is some aspects of the hardware, and what differs also is the user experience, the interface. So from the perspective of machine learning and computer vision, which we're interested in today, it's the same whether you do the Guardian, so a system that's basically an uncrashable car, and Chauffeur, the autonomy. Okay, so beyond supervised driving, so the topic of this talk, right? So why even wonder, why go beyond supervised? So how many of you have seen this? All right, a few, okay? So I'll read in case it's too far for those in the back. So it's an XKCD comic. So to complete your registration, please tell us whether or not this image contains a stop sign. No, yes. Answer quickly, our self-driving car is almost at the intersection. And I really like so much of AI is just figuring out ways to offload work onto strangers. So you know crowdsourcing and all these kind of things. That's how supervised learning works. And crowdsource, so you know like XKCD has these secret alt text, right? You can, secret, not all of it. Crowdsource steering doesn't sound quite as appealing as self-driving. Okay. So another, like more for real reasons, again, as I said, Toyota is like 100 million cars on the road today. Obviously, average life of the car is like 14 years, so a lot of them are old and don't have like fancy sensors or compute. But eventually they will all of them will have. It's like 10x YouTube in terms of data, right? If you imagine current production cars, right? Without fancy sensors, with just camera, radar, CAN, like so the information about the car sensors itself. It's like if you do a really very, very conservative back of the envelope estimate, it's 10x YouTube, right? In practice, it's going to be way, way more than this, but I don't put the actual numbers because it will scare you. So how do you even hope to make sense of all that data? Well, it's robotic data, right? So at TRI, really our perspective is about robotics. And so it's data that is structured, okay? So that's the hope. But the thing is it's unlabeled, right? So how do we learn with structured but unlabeled data? All right. Another thing is, okay, let's assume you are a very large tech company that has started before other people, or you are an Israeli company that has started way before everyone else in that field. And you just say, all right, I'm just going to hire as many workers as I can, and I'm going to label as much as I can, and that's going to be good enough. Well, there's an interesting, very interesting presentation by Ed Olson at CVPR this year, where basically he compared the current rate of progress of supervised learning with genome sequencing. And actually what it shows is that even if you assume the exponential rate of progress, right, the doubling, then it will take something like 19 years to reach an acceptable, potentially acceptable, let's say the lower bound of acceptability of performance, okay? And if you look at the genome sequencing, it's kind of a similar thing happened where you see on the curve on the right, there was an abrupt decrease in costs for genome sequencing, and that's because it introduced an entirely new technology, right? So we need this kind of like leapfrogging to happen, and it won't be just with more labels. Okay, so that was just like all intro to get you prepared and warmed up. We'll talk about specific challenges on long-term large-scale autonomy, and then we'll talk about two really recent papers that we did in my team that just surfaced on arXiv, so it's like really hot off the press. One's called SuperDepth, and the other one is called SpiGen, and there are two kind of like different ways where we're thinking about the problem of going beyond supervised driving. So first, long-term large-scale autonomy. So for driving, so I don't know if you are very familiar with autonomous driving or not, but there is the Society of Automotive Engineers, SAE's level of autonomy. So you probably have heard about level 1, level 2, level 3, level 4, level 5, etc. That's somewhat controversial. It's really hard to interpret. It's not clearly functional. I keep forgetting the definitions all the time, so I proposed another definition, which is more or less accurate. So level 0, you drive, right? Level 1, take the feet off, right? So for instance, adaptive cruise control does that. Level 2, hands off, so lane keep assist, or at this stage you would say like autopilot, like Tesla. Hands off, all right? So then eyes off, right? You take your eyes off, so meaning you don't have to monitor constantly the system, right? Which you have to do with current systems. And then brain off, meaning you can actually fall asleep. And then level 5, you off, meaning that the car doesn't need a person inside, right? It doesn't need to wake you up from your nap saying, by the way, we're stopped in the middle of nowhere because I don't know, something happened and you need to take over, right? So that's kind of like to show you the challenges. And we want to really go to that point where we have a robotic car that's completely autonomous. And so this is Emilio Frazzoli, which is the CTO of New Autonomy, one of the legends from MIT on the DARPA Urban Challenge. And he's basically talking about the space in terms of if you want to do full autonomy, you have to do very geofenced, very limited. But we really care about everywhere all the time. And of course, it's not going to happen in a year, right? So what are the challenges? Why do I say, of course, it's not going to happen in a year, right? So specifically for anywhere, anytime autonomy. So for long-term autonomy, you have several different problems. You have first the problem of how to select data from a continuous, unlabeled video stream or sensor stream if we use LiDAR and things like this. So there's multiple different research options and problems that are being studied by the community, right? Number one is learning from interactions, so disengagements. So this is called, typically in the field of imitation learning, right, is that you have demonstration, then the system does something, and then the human corrects it. So immediately you have an error measure. It's also called behavior cloning. So unsupervised, if you really want to just say, hey, here's a lot of data, just tell me what data should I label, for instance, right? And you have these active learning, but you have like in the unsupervised space, you have just at the first level, you can detect anomalies, changes, like weird things basically, and have a proper formal definition of what weird means. And self-supervision, right? And self-supervision is really interesting because it can basically find supervision, and you can use your traditional arsenal for supervision, but using labels that are automatically derived from the data, right? And in the case, for instance, of driving or navigation for robots, SLAM is a really interesting and well-known problem, and you can use loop closures, for instance. This is work by Sudip Pillai in my team. Okay, now, how to continuously update data, right? So for again, long-term autonomy. So imagine you have a robot that will just go around endlessly. There's another great XKCD comic where they have a roadmap for autonomous cars, and they say somewhere in 10, 30 years, the car will just wander off aimlessly without ever stopping, and then you'll just see it because it will be a charge on your credit card. So how do you update continuously, right? So lifelong learning. There's the problem of catastrophic forgetting, right? But also there is this notion that there are things that you want to forget, right? And there's this interesting like old school papers by Jan LeCun called optimal brain damage. There's a typical also problem in adaptation, continuous adaptation of drift, right? So is that a new pattern that I should memorize, or is that just noise? So this drift versus new pattern problem. Without manual labels, it's really challenging. And again, if you're talking about going beyond supervised, that's a key problem. And then you have unsupervised domain adaptation. How can you do it online? And that's the last part of my talk. I'll talk about this a bit more. Okay, for large-scale autonomy, you have, so large scale this time is imagine you have like world scale, many, many vehicles everywhere around the world. And so for anywhere, anytime autonomy, you have an interesting question, right? In this era of deep learning and twin learning, you have, is there a single unique representation of the visual world that I can act upon, that I can make planning on, etc.? Or should I have a mixture of experts, right? Or should I have a base representation that I can adapt as needed? Another one is, again, unsupervised domain adaptation. So can I just update the model? How to capture the heavy tail. So the heavy tail is really something important. This you might know this data set, the Mapillary Vistas data set. So it's one of the largest semantic segmentation, if not, I think the largest semantic segmentation data set in a driving context, so crowdsourced from end users that upload images from all over the world. Has some crazy images. It's really interesting. You have snow. You have all kinds of very difficult conditions. They organized recently a competition with Facebook at ECCV, and we finished second on that competition. The plot on the right is also interesting. It's from Airbus. It's an analysis of average accident rates for the flights. And what you'll see is that with every new generation, the accident rate is worse than the previous generation, because the previous generation was very bad, but then with time, the edge cases are found and fixed. But then the new generation is introduced, which is supposedly better, but it's worse until like there's sufficient data to actually work out the edge cases. In the machine learning space, now there's an interesting question, which is where do you put ML in that, right? So what's ML's role, right? And there's something I call this the spectrum of ML entanglement, right? Which is you have on the left side, you have the supervised learning, right? So, and we have this thing called Newton plus Hinton in the team. Engineer what you know, learn what you don't, which is an expression that I think came from Stefano Soato. So here you have, very interestingly, in the driving space, in the 80s and 90s, you had Daimler, so Mercedes, had a very modular vision-based system that drove autonomously on the highways in Germany. So very engineered, with some learning, but very, very engineered. And then on the opposite of the spectrum, you have Alvin, right, which some of you might have heard of. It's Dean Pomelaw's NIPS work, where they, CMU, where they basically had a single neural network drive a car. And in the middle somewhere, there is representation learning, right, which spans a broad spectrum across these two extremes. And this notion of separation principle is kind of interesting. So in representation learning, right, there's can the representation be better than storing the data, right? So that's a fundamental question you want to answer, and you'll see why. So the question is no. The answer is no. Okay. So the medium answer is the data processing inequality, right? Which is generally translated as garbage in, garbage out, or in a more information theoretic, it's related to entropy. Post-processing cannot increase information, okay? And there's a longer answer, a bit more involved, and also a bit more speculative, because it's just theories at this stage. So it's the theories of deep learning generalization, right? You know, it's like one of the big quests right now is deep learning works. Why? Not completely sure. So understanding it is really valuable. So there are some theories that have some merits. And the one that I personally favor is the information bottleneck. And again, like Stefano Soeto has a great paper that I recommend, Separation Principle in the Age of Deep Learning. And they are all kind of like basically lead to this, we need scalable supervision or high sample efficiency, all right? And here in this talk, I will talk a little bit more about that first option, because the sample efficiency is very difficult. It's kind of a very open problem. And I know actually at UVA, a lot of people, including some people here, have worked on one shot, zero shot, few shots, these kind of things. I am more on the scalable supervision, either via simulation or via self-supervised methods. And that leads me to self-supervised. So, so this paper, which is on arXiv, you can check it out. It's called SuperDepth, Self-Supervised Super-Resolved Monocular Depth Estimation. And it was done in my team really recently. And so, as you know, I think some of you, again, have worked also on self-supervised learning, I'm sure, but I'll just lay it down quickly. So you have your raw data, right, that feed into a model, and you get predictions, right? That's obvious. Now, curating labeled data for that is tedious, difficult, expensive, you know, like especially semantic segmentation. I don't know if you ever labeled the semantic segmentation image. Sorry, I went fast. We of course do some supervision, right? You always need like labeled data for instance, for testing, right? It can take up to 4 hours per image for like really complicated driving scenes, and it's for people that are well trained with a good interface. So it's kind of crazy. And for cars and robots, you know, large volumes, again, of unlabeled but structured data. So we can go beyond that. So here in the case of self-supervised learning, you combine raw data and prior knowledge to get labels and constraints, right? And then these labels and constraints can be used to formulate a loss. And that loss is basically used to do standard backpropagation and what you're used to. And the thing I highlighted in blue are where this novelty is, where the research is happening right now, right? They're in how you combine the data and prior knowledge to get labels and constraints, and how do you define the loss. So, yeah. So in the case of, for us, right, in that particular work, what we want to do is understand the depth in the scene, right? That's obviously very useful if you want to do collision avoidance, if you want to do mapping also to do registration, localization. And why do we care about this depth from mono, right? So specifically, I give a camera, I feed it into a model, it produces me a depth map. We care about that because, for instance, it could be an alternative or complementary to LiDAR, right? So LiDAR, you know, is this crazy expensive sensors with lasers that turn around and that measuring the time of flight can give you a 3D point cloud. Very used in driving at the moment, like autonomous driving is really reliant on this. Or multi-camera rigs, right? So not all cars, especially production cars, have multiple cameras, and in large-scale industrial context, like for many, many, many cars, the economy of scale makes it sometimes difficult to put many cameras in the car. It's also more versatile. You have a single camera, you can use it. And it can be also in a more deep learning stack for autonomous driving, because obviously we're putting a lot of deep learning in the cars. These if you have a network that can do this, it can be mutualized, meaning that you can share an encoder, for instance, so you can have multiple networks combined together. That's like one of the benefits of deep learning is that different parts of the stack in deep learning in terms of software are actually really close and easy to merge. And so in the case of self-supervised monodepth, what we use is we use geometry as prior knowledge, and using the camera and geometry, we elaborate geometrical constraints, right, using in the form of view synthesis, right? And I'll detail that a little bit. And that's how we can basically get a loss that is self-supervised by using geometry. It's really interesting what's happening in deep learning these past 2 years, where you had this computer vision was very geometry focused, and then you had deep learning that throw that all away. And now we're really entering an interesting area where the two get combined, right? And what used to be the geometry that makes you your output, your solution, now geometry just provides you a constraint that you can use to learn a model that makes your predictions. So in a bit more details, so self-supervised monocular depth estimation, we didn't invent that, right? So you might be familiar with certain papers, especially Zhu et al., or more recently Godard's paper and CPR 2017, which is what we're starting from. And so we have, in particular in this case, to use the geometrical constraints at training time, we need a stereo pair, right? So at test time, we just feed a single image and we predict the depth. But at training time, to be able to self-supervise the system, we have a stereo pair. And we're using the geometrical constraints, right, epipolar geometry, to constrain the learning. So how do we do that? So we feed the left image into a network, and we use DispNet, right, which is a disparity, is an architecture that works well to predict disparities from Brox's lab, CPR 16. And so what it does is that network produces us a left disparity map. And from that left disparity map, we can synthesize the right frame, right? So like using geometry, right, and using calibration, like a calibrated stereo pair, we can basically, from the left disparity and the left image, warp using spatial transformer networks. So in a differentiable fashion, we can warp the left image onto the right image, okay? And then what we can do is we can basically just compare the warped left image and the right image, okay? And they should be the same, right? And this is called the photometric loss, okay? And this is the standard approach to use geometry for self-supervision in depth prediction from Monocular. So what we do in particular is we have this complicated loss. So again, it's a lot about loss engineering. And so you have the overall loss has 3 terms. A multi-scale photometric appearance loss. So this is the standard loss, now standard for the past 2 years in that space. So where you basically warp the image and then you pay a cost that's based on the structural similarity index, SSIM, plus like a simple direct comparisons. You have a disparity smoothness loss, which is edge aware. That's classical, again, vision tricks to improve the look of the disparity map. And you have also a weird occlusion regularization term, which is just you minimize the L1 losses just because you don't want to, you want to basically have some kind of bias in your foreground and background disparities. So that's more like a trick to make it work on driving data. So now, one of the things, so far there's no new contribution, right? So far that's more like a primer on self-supervised depth from Mono. One thing we found that was hinted somewhat in some papers was that resolution matters, meaning that we did a study where we increased the resolution substantially to high resolution, and what we found is that on the right you see a plot with some accuracy metrics, so some are higher is better, some are lower is better, and as you move right you increase the resolution, and what we found is that just simply increasing the resolution from this standard baseline yields almost state-of-the-art performance. So it just improves. And so we started to wonder, well, what if we apply super resolution techniques, right? And see if that improves even further. And so that's why it's called SuperDepth. because it's super resolution applied to depth from monocular estimation. And so you see here, one thing that we found was pretty important. So super resolution, for those of you that don't know, is you take an image, and what you want to do is just resize it, but by interpolating or hallucinating, if you want, the details, right? And it works really well with, again, like self-supervised deep learning. Why? Because you just take a high-resolution image, you downsample it, and there you go, you have a training pair, right? The low resolution and the high resolution. And you can train networks. Now, it's used generally for compression and things like this, right? Because you just have your high-resolution image, you downsample, send it over the wire, upsample on the other side. There's a lot of tricky details about super resolution. One of them that's important is how do you upsample, right? So the networks are typically encoder-decoder networks. And in the decoder phase, there's a learned upsampling. Now, what we found was really important is using sub-pixel convolutional layers, where the idea is instead of the traditional approach, which is resized convolution, which is you just do nearest neighbor upsampling or bilinear upsampling, and then you feed that through a one-by-one convolutional layer that will just learn to refine that, right? Using sub-pixel convolutions is actually really important in our case. It does smarter upsampling. The way it does is by having this like pixel shuffle or interesting, let's say, equivalence between spatial dimensions and channel dimensions, right? So what you can do is you can say, well, I will predict at the same resolution, spatial resolution, right? But what I will do is I will predict many more channels or many more feature dimensions, right? And actually, you'll predict R² feature channels. And then you will rearrange the pixels from depth, right, from channels into space, right? And you see this is this interweaving thing that's happening there to basically upsample. So you're trading off like depth for space. And this is how you can do super resolution at lower dimensions via upsampling like this. Again, as I mentioned, like encoder-decoder, I won't go into the details, but this is the standard encoder-decoder plus our sub-pixel convolutions in a multi-scale fashion. So again, being multi-scale is really important. That has been always the case in computer vision for the past, I don't know, probably since scale space theory, so like 60s or something. Another trick, so yeah, deep learning, as you know, many tricks. It's really important, and you should talk about the tricks. They're not just tricks, they're part of the algorithm. So we found that something that was also important was differentiable flip augmentation. So because of boundary effects, and in the way when we predict disparities, one thing that is important and that people use at least at test time is they flip the images. So it's like you have to flip them in a geometrically consistent fashion, and then you fuse them, and that enables you to basically overcome some border artifacts. Now, this is done at test time typically. You know, this is test time augmentation, like how we would do like multiple crops in an image and then average the predictions, for instance, if you do image classification. Well, this one is specifically for the case of disparity estimation. However, what we did is we just changed it from manual post-processing at test time to an actual layer, to an actual differentiable operation. So it's a differentiable flip augmentation. And again, we use the main workhorse in that space, which is the spatial transformer network. So details in the paper. What's important is that way we can train the system to have this flip augmentation. So it's an additional geometric constraint we put in place. All right, a huge table. I won't go into the details, just to say we did our homework. We evaluated a lot of things. We did an ablative analysis. We're state-of-the-art on almost all metrics, especially the ones that look at higher accuracy. So depth estimation is a bit complex, has many different metrics to estimate. But when you put a threshold on how accurate you want this to be, our method really shines. And that makes sense because it operates at high resolutions. So something I haven't mentioned that you might have not thought about is that for a depth from mono setup, to do this reprojection, you need the pose, right? And so that's why typically you combine both a disparity estimation network and a pose estimation network. And by pose, I mean the pose of the camera, right? Rotation and translation. And so we have also a network, PoseNet, that does the pose estimation. And that actually you can evaluate also as a visual odometry task, right? And so, by the way, I forgot to mention this is the KT benchmark, but that's almost the only benchmark that people use for that. And so here, sorry, you can't really see that well. But one thing that's interesting is that you know that in the depth of monocular, you have an ambiguity, right? You have reprojection ambiguities, but you also have a scale ambiguity, okay? But the reason we're able to do this at training time is because we train from the stereo pair, right? And because the scale of the objects is captured in the network. And that's how we can recover the scale, right? And so we're not necessarily metrically accurate, but we're metrically consistent, okay? And then when you use, of course, the calibration of the cameras, you recover scale. So here you see that basically on some sequences on KT, we actually do pretty good on visual odometry in addition. Okay, so some qualitative results. So here you see, I'll show you a couple, and then a video. So one thing that's of interest is you see that we do fairly smooth, but not over smooth, right? So for instance, over there you see poles and trees, pedestrians, and this is quite sharp. This is a comparison with the state of the art. Again, maybe better to see in the paper really zoomed in, but again, the main thing is that we're crisper at the boundaries without having holes or noise, like high frequency noise or things like this. Okay. The cool thing is when you have depth and you have the pose, you can do localization. And what you can do is you can get point clouds. Really important to visualize point clouds. Why? Because they show, obviously, the problems much better in 3D. So here what you see is you see these video sequences where you see our disparity maps. And they're much more accurate. There are some artifacts on the border still. But if you look at the point clouds, you see that we're doing fairly good 3D reconstruction. And again, from monocular. Only from monocular, no supervision. Okay. So just summary of the contribution of that SuperDepth part. So we use subpixel convolutions for disparity estimation using super resolution techniques, where we replace resized convolutions with subpixel convolutions. We improve the photometric loss with finer details and crisp boundaries. We introduce also differentiable flip augmentation using special transformer networks so that it's trainable. And it improves variance characteristics especially. So I haven't talked in detail about the metrics, but again, I encourage you to look at the paper. And replaces the hand-engineered test time augmentation, as I mentioned. So it's self-supervised, it's scale-aware, and it's monocular. So that's what's really cool and exciting. And then you can literally use all the data with this, right? So, all right, okay. Last part is another way to use all the data, or another way to scale, is to generate your data and your label data, right? So using simulation. Okay, so simulation is great, but why? Again, so why do we care about even generating our own data? Why, again, why don't we label just all the data? For the scale of the problems we're talking about, and that's why I spent the first part talking about driving and like a lot of time like motivating the problem, we know we can't label all the data. Everybody knows, like not TRI can't label the data. Nobody can, nobody. And so there are studies on this, right? And this study is surprising because it's 2016, and it's, I think the first time I saw it mentioned was by our CEO, Gil Pratt, and very few people actually mentioned it. We know that, there's this question of how safe is safe enough, and there's an entire question about, like, societal question about acceptance of robots taking safety critical decisions and risking to kill people, even if they save many more, right? So there's this question of how safe is safe enough. Is 10 times safer than a human safe enough? Is 100 times safer than a human safe enough? There's all interesting ethical dilemmas related to that. But setting that aside for now, even if we accept that just 10 times better than a human is enough, we need trillions of miles. because we're making a statistical, like a statistical robot, right? It's not a robot that has equations and that is just pure control. It's where everything can be proven and given guarantees. We are talking about a robot that senses, uses statistical model to recognize patterns and acts upon it, right? So it requires statistical testing. And to be able to prove, statistically speaking, that it is 10 times safer than a human, you require trillions of miles of tests. So obviously you cannot build a test set of 1 trillion miles where you have every semantic thing labeled in the world. It's not possible. So the trillion-mile challenge, right, is basically means you require simulation. So, and again, if you think about it in terms of like, just forget like the labeling problem, right? Just think about the data problem. Right now, everybody that has test cars can do millions of miles and collect millions of miles. Ordinary drivers, most of driving for ordinary drivers is boring, right? Straight on the highway, etc. So same thing, if you downsample, if you look at these, it's going to be millions of miles. So you need billions of miles in the simulator to be able to test. I won't go into the details. When you hear simulator in autonomous driving, most often you hear simulation of situations, not simulation of the sensor, simulation of the world. We have a contrarian view where we really want to simulate the world. Like, think the Matrix is our ideal simulator, okay? And so SpiGen is a method that enables you to do unsupervised, again, the point, sim to real adaptation. And so, again, it's an Monocular submission. It's just on archive as of this week. So here the goal is we want to learn using simulation, simulator privileged information. So we did, I personally did a couple of papers, and also our friends at CVC did really interesting papers around simulators. But the main thing that's interesting that has not been really leveraged is that a simulator is not just giving you XY pairs. It's not giving you an image and a label. A simulator actually works by having a strong notion about rendering equations, physics of light, about physics equation, dynamic simulation, etc. So internally, there's a lot of knowledge inside the simulator that we're throwing away when we're just looking at the pixels. So we want to leverage that privileged information, whether depth, surface normals, forces, material properties. And how do we want to leverage it? We want to leverage it to basically go from a simulated image, right? And of course, if your simulation was perfect, you wouldn't need that. But simulation is not going to be perfect for a long time. So in the meantime, you have to address the domain gap. And so you want to go from a simulated image, improve the quality of the simulation, right, if you can, and statistically, right, if you cannot with just your simulator itself, and use some intermediate internal representation as privileged information during training to help you do a better job at semantic segmentation, for instance. I'll skip the related work. There's a lot of work on that. So that's our architecture. So that's the SpiGen architecture. So GAN, generative adversarial networks. We use an architecture that's a bit hairy. I'll decompose it. But in a sense, it's going to be doing what I said, which is adapt an image from simulation by using a GAN, which is the top part, and then at the same time train a task network, so the network that you want in the end, which is semantic segmentation, but trained only in simulation and with unlabeled real data, so no labels from the real world. And then we have also a privileged network that acts as an auxiliary task. So the overall loss is again, it's all about loss engineering, right? Loss engineering is the new feature engineering. And so we have multiple components. We have an adversarial loss, a task loss, a privilege regularization, and a perceptual regularization. So the adversarial loss in details, what we use is we use a least squares GAN as GAN, right? It's more stable in training, and it generates better results in our experience. So that's going from a synthetic image to a fake image, and then using a discriminator from unlabeled unpaired real world data to basically learn how to generate better fake images. So that's standard GAN, and I'm sorry I don't have the time to introduce GANs for those of you that don't know, but hopefully you get the intuition. Then we have a task loss. So in our case, for that paper, the task is again semantic segmentation. Take an input image, predict the semantic labels. And so we use standard cross entropy. Here the difference is that we have two cross entropy terms. We have one for the synthetic image. So we learn a network on the synthetic data, but obviously this one will not work well on the real data. So the adaptation happens because we also learn on the adapted image, right? So we learn on the generator output. Now, this makes a subtle assumption that we discussed in the paper, which is that the label, if you see YS on the left side and YS on the right side, are the same, meaning that we assume that the generator is label preserving. So if you refine the synthetic image with the generator, then you assume that the labels are going to stay the same. And then we have our core contribution, which is the privileged loss, right, which is an auxiliary task, which basically what it does is it will train a network to predict internal data from the simulator, right? And what you're saying is that the simulator knows that this is true about the scene, for instance, the depth, right? So the depth from the Z buffer is probably the simplest privileged information that you get from any simulator, because the simulators generate things in 3D, and they can tell you for free the 3D information, right? And so here, what we do is we say, well, train a network together jointly with all the rest as an auxiliary task to say that this is the depth of the scene, and if you're not able to predict that, something's wrong. Same thing here. The subtlety is ZS is the same on the two sides. When you predict the depth from the synthetic image and when you predict the depth from the refined image, the fake image. So you're also assuming that your generator is going to be depth preserving in that case. And then we have another term, which is more a traditional term, which is the perceptual loss, which is more like content preservation loss. So this helps, actually, this is an important technical detail in our case, because this regularization helps ensuring the label preserving and the privileged information preserving properties. So I'll go quickly on the experiments for the sake of time. We did two experiments. So both using always the same simulated data, which is a standard Cynthia benchmark. And we did transfer to cityscapes. And then we did another experiment where it started from Cynthia, transferred to vistas. I won't talk about the networks. We used some very simple basic network that everybody uses for this comparison, which is FCN. In a nutshell, this works better than the state of the art. Again, this is just to say we did the homework, details in the paper. This works better than the state of the art. And we did ablative analysis to show that it's much better than no adaptation, right? And it's much better than adaptation without the privileged information. Vistas is harder, so the gap is actually bigger. And what's interesting is that, so same conclusions, but the state of the art actually fails pretty badly. And the reason is because the domain gap being bigger, some main approaches like CycleGAN or PixelDA, they basically assume a smaller domain gap, right? And that's why often in these papers they can actually overcome the domain gap fully and perform better than the fully supervised case because they use more data. But if you look at Vistas, because the domain gap from Cynthia to Vistas is much bigger than from Cynthia to Cityscapes, there is a lot of negative transfer going on, meaning that some images that are worse after adaptation. And so in Vistas, what we found is that we actually, thanks to our regularization, do much better on the negative transfer. Okay, examples of how it looks with adaptation, without privileged information or with privileged information. Again, in the case of Cityscapes, not obvious. But in case of Vistas, you can look in the paper, there's some degeneracy going on because it fails to adapt versus our privileged information that works. Some results for semantic segmentation. These are all in the papers. You can see how well it works after adaptation. And to conclude, so I talked about the long-term large-scale autonomy challenges, right, at first. So I talked about unsupervised adaptation quite a bit. Lifelong learning, self-supervision, learning from interaction, and the robustness to the heavy tail. I hope I convinced you that these are well-foiled problems to study in the community, and a lot of people in the community are already studying those problems. And beyond supervised driving at TRI means the SuperDepth that I talked about, so self-supervised depth from mono. The GAN that I just talked about, SpiGen. And in terms of, we really care about this, so that's what's really, really cool about all this right now, is that this is used. This is not just useful eventually to someone someday. This is useful right now to us. So you get to work on problems that are really exciting scientifically speaking, and you know why. So that's the cool thing. Learning from structure and label data, Newton plus Hinton, and that's it. So thank you. And if you have any questions, I'm happy to answer them.
Any questions?
Yeah. Yep. Yes, but you learn it, right? So the difference is that it's not just a post-processing, right? It's not just like if you were indeed just doing bilinear upsampling, for instance, yes, you're correct. But in that case, it's part of the network. You actually learn patterns, right, to super resolve. But then the difference with super resolution is that in super resolution, you would actually penalize the network for not super resolving the appearance. But here, what we super resolve is the disparities. And then we super resolve the disparities, which enables us to do the reprojection and the photometric loss at high resolution, the original input image resolution. Because otherwise, it gets downsampled, and then you do it at the low resolution. So it's a really good question. All over the place. We're across the spectrum because like it's so huge, right? Toyota's efforts are really, really big. So you have things in the car right now. So you have something called TSS2, Toyota Safety Sense 2, which is in all the cars. So whether you buy a fancy Lexus or like it's called LSS or like Lexus Safety Sense or whatever, it's the same. And these use like your run-of-the-mill computer vision algorithms, like from camera, it will detect pedestrians, it will detect obstacles and things like this. So you have very engineered supervised stack. And then you have, like at TRI, we do a lot of really prototypes. So, and even in the prototypes, we have some prototypes that are very like LiDAR based, the usual like DARPA challenge. So you do clustering of points with LiDAR, et cetera, et cetera. And you have also semantic segmentation with deep learning. You have all these different things. Even in my team, so we're the most researchy at TRI, and I think in the whole Toyota space. We also do end-to-end driving, which also some people that are funded by Toyota here in Europe, especially Luc van Gool's group, that's heading a lab called Trace. That's a joint lab with Toyota. He also does like end-to-end learning. So of course, we're not going to drive a car with a single network, but there's interesting insights to be derived, and potentially that can be one of the many streams of information in the system. So we're all over the place for this reason that we're big, but there's another reason, which is a robotic system perspective, which is the Byzantine generals problem, right? So Byzantine failures are when you have different sensors in that case, right? Or different parts of your information system that lie to you, right? They give you a wrong message. There's a pedestrian here, there's no pedestrian. Or there's no pedestrian here, there's someone here, right? So the only way we know theoretically to overcome that problem is by redundancy, simple as that. So, and then the main challenge you have to solve is how do you fit in the computational budget? And that's where we are.
Other questions? I have a question. So you mentioned that simulation is not just pixels and labels.
Yeah.
There's physics and dynamics, etc. But like, simulation is also about actions, right?
Yeah.
So maybe I missed it, but we haven't really talked about that. Do you
Yeah.
plan to use reinforcement learning or variant at some point?
That's a very good point. So, so one thing that you can do in simulation, you can do in the real world, is crash into things, right? So you can go and have fun and just say, oh, let's try that model. Oh, it killed 1,000 pedestrians, which is better. It used to kill 10,000 pedestrians. Obviously, you can't do that in the real world, right? So you can do that in simulation. Therefore, you can use RL. Inverse reinforcement learning. So there's a lot of work we fund at Stanford, and especially one that's interesting from Stefano Hermon called GALE, Generative Adversarial Imitation Learning. So you can try to learn the cost function, the reward function. There's another, and that's the classical RL kind of like like worldview about simulation. There's an interesting other thing, which is again shameless self-promotion, which is we made a data set on generating actions in simulation. And so here it's the other side of the word action, which is if you want to learn behaviors or if you want to learn to react to behaviors, you have to be able to simulate those behaviors. And then there's two ways to do that. Either you hard code them and you have a set of rules or a probabilistic model, which is what this paper is about. Like this is an anti-GAN paper, right? So it's a CVPR 17 paper that we did with my former PhD students, Cesar de Souza. And here the goal is we say, what is an action video? It has a camera, it has an actor, it has we have skeletal information. And the real holy grail is not to have to hard code this or not hard code too much, have a parametric model of actions, and then being able to learn how to generate actions from that parametric model. So this is, the two sides of the word action, I would say, in simulation. So that's a good question again. So in robotics, you have perception, prediction, planning, control, right? And the deep learning is most used in perception, right? Starts to be used in prediction, so understanding human intent, for instance. Very little used in planning, and then almost not used at all for control. And in the classical robotic stack, right? And if you do end-to-end, of course, there's no stack. It's like one single thing. So perception, it's used very much for perception. Now, for computational budgets, on the perception algorithm side, there's two ways to do it. There is the current main way, which is the expensive way, which is use GPUs, right? And so Toyota has partnered with NVIDIA, and there's some cars that we're making after 2020 that will have some GPUs in them. But still, that's a big problem of power consumption and cooling, right? And long-term operation. And so eventually, you need to bake it into silicon, right? And you have a lot of accelerators and things like this. The problem is it's too early to bake it into silicon right now because, all right, quick, VGG 16 or ResNet 50? What do you want to put in the car? And it has to be one or the other. And ResNet 50 has to be exactly that number of channels because that's what has to be baked in silicon. So there are some solutions in the middle that trade off this. But again, there's a spectrum from very general compute to very, very specialized ASICs and stuff like this. And right now, we're more on the general compute side because we don't know. I mean, that's why we're doing research. And watts is the main problem. Watts is the main problem. So the ratio of, let's say, TOPS per watt is a typical metric. It's a bit of a misleading metric because you also have the algorithm has more or less affinity. It's a very broad topic. We can talk about it later.
Max Welling actually was giving a talk in ICML where he talked about intelligence curve.
Uh-huh.
So that's very well.
There you go. There you go. Yeah. Yes? Yep. So training with stereo, but what you train is a network that can predict depth from a single monocular image. So at test time, you evaluate by feeding a single image. But the training is stereo. So that's an interesting question because ideally, you would want to train from monocular, right? And we can train from monocular in our setup, but then the loss is slightly different. Of course, you can't leverage that strong geometrical constraint of a stereo pair, so you can't leverage the epipolar geometry there. So you have to leverage other assumptions. And there you are hitting fundamental problems in terms of reprojection ambiguity. So the classical problem in driving is, imagine you're driving, you're this car, right? And there's a classical setup where you're going straight, but the car in front of you is driving at the same limit, same speed as you, because you are both driving at the speed limit. Now, that car is never getting closer to you, right? So its pixels, basically, are going to be, could be reprojected at infinity. So that car is never getting closer, so it's like if it was painted on the sky. And that's why typically if you train these methods on purely monocular, what happens is you have these holes where the car is, if it moves exactly the same speed as you, because from the reprojection error perspective, that car is infinitely far. And solving these problems requires most likely semantics to help.
We have time for one more question.
Okay, so there's two it's a really good question. There's two interesting sides to it. There's one which is I disagree with your premise, and another one which is more interesting, which is a machine doesn't necessarily have to be a human, like behave as a human. Right? I strongly do not believe in AGI, like, or at least if it happens, it's like so far in the future you can't predict it, right? If Hinton says he can predict the future 5 years later, and people say it's going to happen in 30 years, you know what it is. It's bullshit. Okay, so driving is not AI complete, right? It doesn't require you to be able to have a robot that can cook pasta so that he learned what is hot or what is not, and then he can blah, 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 and then he learn how to drive, right? It's not AI complete. You can reduce the problem to certain specific tasks and then learn that. And you can have mathematical models that could be bio-inspired or not, but they are optimized for the task. So they don't have to be AI inspired. Now, I said I disagree with your premise because of theory of mind. So we do not experience a crash, maybe physically, but we know what a crash is. We heard people tell us about crash. We might have even seen images of crashes, most likely. And therefore, in our head, we have this game engine in our heads. That's an expression from Josh Tenenbaum, which means we have a simulator in our head which we can imagine ourselves, right? That's the base of empathy, is you can imagine yourself in a crash. And you can be scared about it. And you can even imagine it on the spot when something is about to happen and you're about to crash. And you can even imagine what would have happened. So this is kind of like, actually this is used in, I'm a climber, I like to climb. This is actually used by professional athletes. It's called mental training, and there's neuroscientific evidence to show that if you're thinking about something, it actually activates your sensory motor circuits in a very similar fashion than if you were doing it. So that's also why I disagree. We do actually experience crashes, even if we're not physically in a crash.
That's a very interesting answer. And let's close with that. Let's
Okay.
thank